All right, so as I was saying over there, yeah, you turn right or you turn left out of your house. Let's say 60% of the time you go right, 40% you go left. You'd be kind of an idiot to go basically half and half if there was a 90% chance you run into traffic or light traffic going this way, and only a 10% chance you get heavy this way. But if you go this way, it's going to be, what did I say, 50-50, I think. Okay, so this right here represents 0.9 is the probability that you get light traffic given you went right. Okay, that is a probability that is a dependent probability. In other words, it's going to depend on what your decision was, what you did. Okay? And so in that regard, that's what the dependent part looks like. Now, dependent on what? Depending on the fact that you conditioned it because you went right off the bat coming out of your house. Okay? So keep that in mind as we go along. That's the same thing can be said for all of those guys. Now, when you draw this tree up, well, I don't know if you guys can see something maybe in the room. Yeah, maybe that's better. I don't know. So what you want to think about is this, is that each one of those can be done up that way. Okay? So that's the conditional probability. That's what that piece means. But the probability that you go right and get light traffic of course is 0.6 times 0.9, or in other words 54%. This is right here. If you go from here to here and then out to here, this happens 54% of the time. Of every time on the planet that you do this, you're going to get 54% of the time you went right and you got light traffic. That means the other 6%, and I got 6% obviously by multiplying, but if you think about it, what we're saying is 10% of the 60% is going to get heavy traffic. 90% of the 60% is 54%, which is, again, so that's the light traffic. That's a total of 60% out here on this end. And then, of course, here, it's going to be 20 and 20 because we're going to split that 40% up both ways. And so here it's going to be 0.2, and here it's also going to be 0.2. And again, these guys better sum up to 40% because that's where we got them from. These guys better sum up to 60% because that's where we got them from. And together, they better add up to 100% when we're all finished. Yes? Now, that's pretty straightforward, I guess. But what I want to talk about tonight is that oftentimes we don't necessarily know what the actual percentage is back here on the front end. Okay? A lot of times in life, what we see is we see this outcome. We have collected data and we see this outcome right here. Okay? And we know that outcome, and so we have a pretty good idea of what percent of them, come from back here, this percentage here, so we can kind of work our way back to that initial value over there. Okay? That's a little thing we like to refer to as Bayes' theorem. Now, the question is this, and this is the kind of question that Bayes came up with. He says, listen, what is the probability that I go left, that I went left, I should say, given that I received heavy traffic? Notice how that's backwards. Okay? What Bayes said is this, based on what I'm visualizing now, or what I'm seeing, can I work backwards and see what percent of the time I came from, in this case, went left or went right? And that was it's kind of a backwards spin on things. The idea that if I know this and I know this, obviously I can get this direction. The question, though, is better. It was often, in the real world, I don't know what that prior distribution was. That's what it means. I don't know what that distribution was, but I know what I see over here in my statistics. And so based on this, and I can work backwards and see if I can get back to what I have over there. That's the whole point of Bayes. Now, check this out. If all I saw was heavy traffic, how often did we see heavy traffic down here? Well, there was
100%.
Almost. So here's the deal. I could have gone left and experienced heavy traffic. Or I could have gone right and had heavy traffic. Those are the two things that could have happened. In other words, I'm not interested in light traffic at all. It's the same way when you go to a doctor. You don't go to a doctor if you're healthy. You know, like I mentioned before, it's people that people get so weirded out about things and statistics, and you're like, just calm down. The reason that they're studying that, the reason that doctors study sick people is because, well, this is what they do. They work on sick people. They don't work on healthy people. That's just not their game. So, well, what about the healthy people? What about them? They don't need a doctor, all right? And what about the car that's not broken? They don't need a mechanic. So we're only interested in ones that have issues, of course. So given that I've had issues, right? In this case, given that I had heavy traffic, what's the probability that it came from the left side? And so the answer is, it's this guy right here. It's left and heavy. Okay? So if you do this, that's going to be 20% divided by, again, that's 20% plus 6%. Or in other words, about 20% out of 26%, which is 90 some odd percent. Well, I suck at math. Okay, I lied to you. It's 77%. In other words, there's a 77% chance, or 77% of the time when I've had heavy traffic, it's because I went left in this case. Okay. That's how Bayes' theorem works. We're going to give a couple more examples of them and how they work and what they tell us. But again, the biggest deal with Bayes' theorem is going back and trying to get an idea of what the prior distribution was, and another part of it is to see how likely something is to have happened. For instance, this happens all the time in drug tests. The classic on a drug test is Bayes' theorem. Okay, we'll do one of those in a jiffy. You know, some years ago, Lance Armstrong got busted for doping, and so they did his test. He tested positive for dope, so they tested him again. He tested positive again. Well, the likelihood that the test was wrong twice is basically non-existent. Okay, there's almost no way that you could have gotten 2 bad tests in a row like that. Okay, so it's almost 100% accurate to say that he was on dope. Either one of those tests could have been wrong, but the chances that both of them were wrong pretty slim. Okay, because that's what would have happened in that case. Okay, so there's this guy here. Here's another piece of that. You got everything? Oh, you want to wait? I'll wait. I get too excited. Bayes, B-A-Y-E-S. And we'll actually, after we do a few examples of this, I'll show you. It's a pretty sweet video done recently where they showed exactly how he went about his initial proof of this thing. Well, it wasn't a proof originally. He was like, hey, that's interesting. And then based on that, then he came up with this theorem. Okay, so it's a pretty cool experiment. And it was on one of those math channels that I watch from time to time on YouTube. And they just did an example of it the other day. I thought it was pretty interesting. Another one, again, is this idea of, say you're just testing for drug use, and in a certain community, maybe 20% are drug users, 80%, of course, non-users. And it's a fact that drug tests behave differently whether you're positive or negative. So if you use drugs, it might be accurate, and I'll say users, I'll put it positive. It'll test positive 98% of the time or something. It'll give you a false negative, like say 2% of the time. Okay, it's never going to be perfect. It can't be perfect. This is how these things are, but it's pretty close. Okay. Now, if you are negative, it's going to behave differently. It's going to test you positive, which again is wrong, but it's going to test you positive, something like this, and negative, which of course is accurate. Let's say 95% of the time. Now, they're both in the 90s, but they're not the same. It never works that way. They're never the same because your body chemistry affects the test or works with the test differently based on whether you're on drugs or not. So the question here is this. Again, 98% of 20% is something that I don't know the answer to, but I do know that 2% of it is 0.4, or 0.04, Jay. There you go, 0.004. I can't do math. Better use a calculator. So 0.98 times 0.2. 19.6% up here. and 0.4% down here. Okay, again, they better have to 20%. And then here, 0.8 times 0.05, 0.04, so 4% here. The other 76% go here, right? Nice. So the question is this: if a person tested positive, what is the probability that they tested positive given that they were negative? So this is tested positive given that they were negative. Okay. So what had to happen first? Okay, so I'm sorry. I lied to you. What is the probability that they were negative given they tested positive? That's the question I want to ask. You see the difference there? Okay? Because I know what I saw. I know that this guy tested positive. That's what I know. And I know in this community we have about 20% drug use, let's say. So if I know that's true, then based on those presumptions, and I know in the lab I've seen what happens when I run these tests on people that are known drug users and known non-drug users. So based on those results, I can tell you what is the likelihood that this person tested negative, or is negative, given that he tested positive. Okay, it's a very slim chance that happens. So what's going to happen is this. You would say, all right, well, what could have happened? Well, he tested positive, so that's this percent here, plus this percent here. Right, those are the 2 times when he tested positive. And I'm interested in this one here, that is, he is negative, but he tested positive. Okay, and so that would be 0.04. What's that?
Divided by 0.2.
Yes, 0.04 divided by, oh, that's 0.236, isn't it? My math's not been very good today either. So about a 17% chance, there's roughly a 17% chance that the person is negative given that he tested positive. Okay, now that's kind of high. I've been getting those data and those numbers I just made up. Is that, what?
I think it's 0.2 in the denominator.
No, it would be 0.2 if it's 0.004.
All right, yeah.
That's okay. Yeah. So that's the idea behind those. Okay. So when someone says, "Yeah, I feel very strongly that I was falsely accused" or whatever, this is the kind of thing that they go back to. Okay. And again, you can't know for sure. That's why they test them again. Okay. The chances that you would be wrong twice are pretty slim. Okay. And so again, that's the only way that. Oh no, I swear, just because I got 3 false negatives, or 3 false positives in a row, I'm totally innocent. No. And don't ask for another test because you're just digging yourself a hole at this point, all right? Because there's very little chance that you could have multiple false negatives. There's very, very little chance that would happen. Or false positives, rather. Okay? And again, that's just it over and over and over again. So this is a situation where in Bayes' theorem we can say, well, these are pretty well known from statistics from studies in the lab, very controlled environments. These things here, be a pretty good idea of what the community is like. Pretty good idea what the community is like, based on drug arrests and this and that and the other thing, right? So you maybe a pretty good idea of this. But oftentimes you won't know that. Oftentimes you won't know that necessarily. But check this out. So you will have another page like this. So it's a different town. X percent, Y percent. And we'll just do users, non-user. And then again we said what did I say here? I forget what did I say. 98 and 2. And what am I at? 5 and 95. Okay. Those are. I think that's what I know. So then, if we're out there and we're doing some testing, whatever, let's say I'm working in conjunction with a doctor or something. Somehow I'm getting tests over here. Maybe I'm taking tests of people that have to take drug tests. By the way, people who have to take drug tests for their employment, I would argue that maybe maybe they're not the same proportion of people who actually use drugs. I mean, in other words, the people who have to take drug tests may or may not use drugs more often than people that don't have to take drug tests in terms of their employment. Now, some of us have to take drug tests for our employment because if you drove semis or flew airplanes and things of this nature, yeah, we want to keep an eye on you, okay? But if you are the person who works at, let's say, there's some jobs that have to have, they make you take drug tests because people they employ are people who probably use drugs pretty frequently, typically. So we want to weed those people out. So now there are people that take really high-paying jobs too, that, or whatever. They're obviously required to take drug tests too. So in certain instances, there may or may not be a higher prevalence of drug use among the jobs who require those drug tests. I mean, obviously, does that make sense? Though there's some jobs where, listen, I got to weed some people out because they're going to apply for jobs. Yeah, we're going to weed them out. But because, and I'm giving them drug tests because specifically I expect a bunch of drug users to apply for these jobs because, you know, it's lower wage or whatever, and that's just what they have, okay? But again, you know, obviously I don't want my pilot on dope. I do not want my kid's bus driver on dope, and so on, okay? These are some things obviously are big deals. By the way, they do not test teachers. Isn't that sad? Isn't that kind of funny and sad at the same time? Yes. There's a couple guys in my school, at the high school, that are...
How accurate are those tests anyway? Because like
They're-
where I
they're
work at
fairly
IKEA,
accurate.
like they test everybody
Yeah.
for marijuana going in.
Yeah.
But like I feel like a third of my coworkers show up to work high on a regular basis.
Yeah, well, there's, you know, there's, you can get around some things, maybe they just got, you know, if you lay off for a few days, I think marijuana gets out fairly quickly. I don't know the exact number, don't have to look that up, but yeah. But you're right, there's some instances, some places you're gonna have a higher prevalence. I found out that there's two guys I know at my work that are stoned as teachers. They have a nice buzz going probably half the time, okay? And which is only humorous when you see them in a meeting because they're just like, yeah, all right. And you're kind of like, dude, seriously? But then there's this one kid, she was house sitting for this one teacher. She comes in, Mr. Grimm, I don't know what to do. I'm like, what do you mean? I went over to house sit for her, and her bong was on the table. And I'm like, nah. I said, yeah. And I'm like, well, does she have a roommate? No. I'm like, oh, well, all right then. And there's a couple other ones like that. Oh, and this one guy, right before the end of school, he just retired. He goes up to me. He's like this old guy, 65, man. He goes, we'd done some work on his car. We just helped him out. We didn't charge him anything. And I was talking to somebody else, and all of a sudden he goes, do you smoke weed? And I'm like, I didn't hear him right. I said, what did you say? He's like, do you smoke weed? I'm like, no. And he goes, but you do edibles, right? And I'm like, no. I'm like, why do you? He's like, well, yeah. And I'm like, all right. It's like I grow my own. I'm like, oh, all right. All right. And then he goes, I make butter out of it. I'm like, okay, why? Well, to make your goodies and stuff out of. I'm like, oh my God, I'm leaving now. It's just bizarre. So when you look into these deals, this is a situation where you might, if you were the IKEA guy, and you might want to know, like, approximately what percentage of the people who are applying for my jobs are dope users. This is what you might get, okay? And so what you could do is something along these lines. Now, what happens if the person tests positive? Do they get another chance? Typically, the answer is yes, right? So if they fail twice, you can be pretty sure they're where? You can be pretty for sure they're on that top line up there, yes? Right?
Fired.
Well, fired, but yeah. So the idea is if they test positive twice, they're pretty much, you can tell, okay, so test positive twice, you're sure up here. If they test positive once and then they test negative, you can be fairly confident that they're here, but there's going to be a few of them up there as well. But you have a pretty good idea of where those people lie. And of course, if they get by the first time, hey, you're hired, and then we're like, yeah, that guy's a stoner, and he'll slip through the system, yes? Now, we just looked at this a few minutes ago. This piece right here, the probability that you are a user and you test negative, it's pretty slim, okay? It's pretty slim. And so, when we're looking at these here, is this, we have this idea that of the people who, just stuck to the chalkboard somewhere. Is it magnet? I don't know. So, what I'm trying to say is this, is the majority of people will be here and down here, yes? All right? So, we're saying that most of the people who test positive will be from this positive group over here, and so you can collect some more data and work your way back to these values over here. Now, By saying that, what I'm saying is this. If you can get a pretty good idea of what these values are, so let's say 77 up here, and let's say that these middle two, let's see here, the positive ones are somewhere in the ballpark of positive. Come on, Jay, you can do this, buddy. Okay, positives. Yes. So they're positives. If we have a pretty good idea, we can get some characteristics here. But what often happens is I just have the test results. So I have the test positive results, and I have the test negative results. That's typically all I'm going to get. They're not going to tell me these things. Okay? And so what ends up happening is a situation like this. You end up with a situation that looks a lot like this. You have x times 0.98 plus y times 0.05. All right? And if a person were to do this, you'd be finding the probability that the person is a user given that he tested positive, and that's all fine and good. Excuse me. So that's fine, and that's great, but that's not exactly what we wanted to know. What we want to know is this. If you think about this, that's not exactly what we want. What we want is this. We said that the probability that you are positive, given that you tested positive, is approximately 77%. Yes? That's across that top line. Okay. If that's true, then that's a conditional probability, and so it's the probability of B given A. So the probability of B given A is the probability of A and B happening over the probability of A. Yes? Okay? So what I have, I have this thing right here is that. Okay? So the probability of A is the value that I'm interested in, which of course is, I had it backwards. Hold on. So probability of B, I'm sorry. This, I didn't write that right. That's to be 98% right there. Sorry, this should be 98% right here. Because that is this piece right here. It's the probability that you are positive given that you tested positive, yes? The probability of being positive and testing positive is 77%, right? That's the farthest number out there on the end. You are positive and you tested positive is 77%. So if you look at this, what we're saying is this. This is come on, give it to me. Stop it. 0.98 is equal to 0.77 over the probability of A.
So wait, what's the difference between the top and the bottom statement? The probability of
You are positive,
and
you are positive and you tested positive. That's 77% of our total population is in that category. Now, the probability that you oh god dang it, these two are backwards too. I'm just having a heck of a day. Okay, I'm on it now. This should say that you are, well, it's not wrong to say that, it's just backwards. It's that you test positive given that you are positive. Okay? So if you are positive, I know this because the test states in its fine print that if you are a user, you will test positive 98% of the time. Okay? So the probability that you do this, that you test positive given that you are positive is 98% of the time. Okay? Now if you solve for this, you solve for the probability of A, what do you get? Probability of A is 0.77 divided by 0.98. So it's about a 79% chance. So in other words, about 79% of our population is users, approximately, according to this data. So if there's 79% that are users, about 21% then are non-users. Right? Does that make sense? I kind of wrote it backwards, and I apologize for that. That's what you use in statistics oftentimes. Now, obviously, as time goes on, you get better data, so then you can run through this data and you can keep tweaking it over time, right? But so in this case, apparently 21% of IKEA want to be employees, or 79% are users, apparently, according to this. It's ridiculous. Yeah. That's how it goes. I don't know. I find it humorous, people too, that always get all hung up on, oh, dope's so great. And then last year, 2 years ago, there were some people that were caught smoking dope while they were taking care of little kids or whatever. And then people were like freaking out. I'm like, wait, I thought it was fine. What's the big deal? I don't know. I'd laugh about it. It's fine. Question, comment, that make sense? So Bayes' theorem is a pretty cool deal because what you'll end up doing in the real world is you'll end up getting data, you'll stick it in, you'll do the math, you're like, oh, it's about 79% this year, this quarter, whatever. You can get more data. What's going to change? The test isn't going to change, yes? The test isn't changing. But maybe you put in some new questions on your things and more things that the people who are applying for your job must jump through, and maybe I can weed out some of the users, yes? So based on what I've done, then the next quarter, the next year, the next whatever, I collect more data. This number here is going to change. This number here is going to change, which is going to then affect this problem right here, which affects this percentage right here, which tweaks it and changes it again and again and again. That's how Bayes' theorem always works, because you know the end product, you know the intermediate step, and you're trying to get an idea of what the original distribution looked like. Because in the real world, that's what we see often, is the end result. We don't see what goes into creating the end result. We just see the end result frequently. Okay? It's kind of a cool deal with Bayes' theorem. You just work your way backwards. It's a very easy process, though, because it's not very hard to keep working it backwards. It really is a little algebra when you're done. Okay? Yes? No? Maybe so? Yeah? All right. Cool. So. Burger, fish, chicken. Yeah, you can do this all day long. It's not a big deal. Hey, look, 60% of the time I eat a burger, 30% fish, 10% chicken. Hey, that's weirdly, oddly different than mine. Okay, that's cool. Whatever. Okay. Based on what you eat, what's happening to your tum-tum afterwards is going to change. If it didn't, this wouldn't be a Bayes' theorem problem. This wouldn't be a conditional probability problem. If my stomach was upset 50% of the time, regardless of what happened, that's independent of what happened previously. Okay? There's 100% of my dinners right there. Apparently, I'm not a vegetarian or a vegan. I just only eat these 3 kinds of meat. That's it. That's all. No fish. All right. No. What was I going to say? No lettuce. Well, I can eat lettuce with my fish, I guess. But no. What else am I missing? No pork. Apparently. There you go. No pork. Okay. Because again, I didn't account for it. That's 100% of my dinners there. Let's say if I eat a burger, I get upset tum-tum here and here. Fish, it's like probably 60 and 40. And this one must be like 0.9 and 0.1. I'm guessing there's probably some reason why you don't eat chicken. Whatever. Okay? When you do this, when you blow this out, you will see that this is, the top one is 12% and then 48%. Because it's at 12% of the time I eat beef and get an upset tummy. 48% I eat beef and I don't get an upset tum-tum. 18% and 12%, which again adds up to 30. 9% and 1%, which again adds up to 10% total. They're all there, yes? So if you did this problem, what is the probability that I had fish for lunch given that I had an upset tum-tum? Okay. So did I say uspet? Oh, uspet. Upset tummy. There you go. Nice. 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 So what had to happen? Well, there's 3 things that could have happened, yes? I could have had burger and upset, or I could have had fish and upset, or I could have had chicken and upset, right? But the one I was interested in is the fish. Okay, so that's 30, it's 18 out of 39%. Or in other words, about 46% chance that I had fish for lunch, given that I have an upset tummy. Okay? I don't know. That's just for me, maybe different for you, whatever. Okay? It's just a random problem. Very little difference to that. The difference is we're just working backwards to figure out where that came from. Another one that's a classic of this is when you take someone who's supposedly an eyewitness to a crime. No, I swear it was a blue car. I swear it was a blue car. Well, it was a dark and stormy night, and it was a kind of a dark alley. Can you be sure? Oh, I am pretty sure, I think. I think. Yeah, no, I feel like I'm pretty confident. So then they take you to a reenactment with you, perhaps, right? And if you can only identify the car as blue correctly, like 50% of the time, the dude's going to walk. All right, he's just going to walk, because clearly there's a huge chance that you could be identifying the car inappropriately, and so we can't trust your eyewitness reports because you could have been off on that deal. In other words, what's the probability that it was not a blue car, given that you said it was a blue car, right? And if there was like 50% chance of that happening, well, yeah, we're not really, that's nice, you're a nice witness, but we're not going to listen to you because you're obviously wrong. If there's a 98% chance, if you like did that reenactment and you got it right like 98% of the time, yeah, okay, the guy's gonna, he's got trouble, all right? Because yeah, you probably got it on. But again, that's a pretty cool deal about Bayes' theorem. Again, frequently it's looked at in a cheap and childish way like this guy here, but in reality where it's mostly used in our everyday lives is this one here, where you're working backwards to find that initial distribution. That's more common of how it's used. Oh bother. Okay, so I'm gonna hit pause on this deal for a second.